Hey guys, welcome back to AlgoYogi. We are doing graph series, and our next problem in the list is number of connected components in an undirected graph. If you have tried to solve this problem on LeetCode, you would know that it's a premium problem, but we are trying to solve it somewhere else, which is LeetCode. That's like another alternative that I've just found. So what we are going to do is solve it right here. All right, because I'm not paying for LeetCode premium. That's a lot of money. Okay, so there is an undirected graph with n nodes. There is also an edges array where edges at ith index has a pair of values a and b, which means a and b are connected. They are neighbors, by the way. So the nodes are numbered from 0 to n minus 1. So given there are n nodes, it starts with 0, so it ends at n minus 1. Now we need to return a total number of connected components. Now tell me, does this problem sound familiar to you? Because it does to me. If you remember solving number of islands, this problem is exactly the same, except the part that in the number of island we were given a grid, a matrix, and we had these connected ones, which were basically islands, and we were looking for those connected ones in the adjacency list. But here we are given number of nodes and edges. So these edges we will be using to make the graph adjacency list, you can say. And then within that we will be visiting these connected components. So let's see how we are actually going to do it. And seeing that familiarity of this problem, exactly like number of islands, it makes it super easy for us to solve. Okay, so here I've taken this example. We are given 9 nodes. That means the number of nodes are 9, but they're numbered from 0 to 8. All right. Here you can see already that the connected components right here, there are 2 connected components, and we have to return the answer 2. But let's go in detail how we will be returning that to. So here, as you can see, we are given all these edges that represents this undirected graph, what node is connected to its neighbors. So if you remember, when we are given edges to create the graph, we create the adjacency list so that it's easy for us to visit all the neighboring nodes of each node. So basically, to visit the entire graph, it makes things easy for us. So what we'll do is I'm gonna just shift this little up, and then let's create graph adjacency list. I'll call it graph, and if you remember, we have already done problems like this. So it's just we're gonna have all the nodes, and then there will be a list next to it of its neighbors. So 0 has 2 and 1 as neighbor. Then 1 has 0 and 2 and 3 and 4 as neighbors. Okay, so if we remember the code for it, like we'll be creating a dictionary, and then all the nodes will be keys, and then we will append those while visiting all these edges. So 0 will have 1 as neighbor and 1 will have 0 as neighbor. So we'll append both values to both the lists. Okay. Now then we can have 2. Now 2 will have 0, 1, 5. These are the neighbors, and 3. So I guess you can do this part. Okay, I'll leave it here. So this is how we'll be creating the adjacency list. Now what we can do is, since we need to visit all these connected components, so I will have a for loop going from node 0 to n minus 1, and then I'm going to visit all the connected components using DFS. So DFS will help me basically if I start my search on 0. So if I start my DFS at 0, what I'll be doing is I will visiting all the neighbors of 0 first, and I will not be marking 0 as visited like now because I'm visiting it, but once I'm done visiting all the neighbors of 0, then I'll mark it visited. But like for now, I'll check if I have visited 0 because I will call my DFS on 0. So well, 0 is not visited. So what we'll do, we'll mark this visited. I'll have a visit set. I'll have a visit set right here. And then I'm gonna start visiting. So 0, I'll mark 0 visited. Then I'm gonna start exploring all its neighbors. And you know what? I'll write pseudocode as we go along. So what we'll do is I will have a so I'll have a count. I'll have count. Count will give me the number of connected components. So I'll have count as 0. Then I'll have a for loop. So for I in range n, and I will call DFS on I. Okay, so if this DFS returns true, then I will increment my count. So count plus equals to 1, and then finally I will be returning this count. But anyway, now that's not the main part. The main part is writing the DFS. So let's write DFS. So I'll have my DFS function, which will take the node and then visit all its connected neighbors and their neighbors and their neighbors, right? And you can write BFS also here if you want. All right. Now what I'll do, if this node, if node in visit, if it's already in visit, then I will return false. Return false, because if I have already visited some node as part of some other connected component, or like, of course you will be visiting all the connected components all together, but like if you already visited, you don't want to count it again. So it will return false. But then once, if it's not visited, then let's put it into visit. I will mark it visit. Okay, we'll mark it visit. And then we'll also visit all its neighbors. So for neighbors, for all the neighbors, I'll call it n in graph. So you'll access all the neighbors of this node from the adjacency list or graph, and then you call DFS on it, DFS and on n. Okay, and then you finally return true. So this DFS in one go, this whole DFS in one go will be marking all of these connected components visit. So let's run it. Let's do a dry run. So I'm going to start visiting 0. I'll mark, it's not in my visit set yet, so I'll just add it to my visit set and then start exploring all its neighbors. So then I will call DFS on 1, and on 1 then I'm going to start exploring its neighbors. 1 is not visited, so I'll mark it visit. Then I'm going to start exploring 1's neighbors. So 2, let's explore 2. 2 is not visited. Then explore 2's neighbors, which is 5. By the way, 2 has 0 as also a neighbor, but like it's already in my visit, so I'm not gonna visit that. I'm not gonna visit back 1 because I've already received a call from there and marked 1 as visited. So now what I'll be doing is I'll visit 5. 5 is not in my visit set, so I'll mark this visit and then I start exploring its neighbor, which is 3. Let's visit 3. So when I'm like visiting these neighbors, I'm calling a complete separate function on these, like because of this boy right here. DFS is calling on all the neighbors. So I'll just go quickly now. 3 will call on 4. 4 is not visited, will add it to my visit set, and then 4 will try to call its neighbors. So it's gonna try to call 1. 1 is already visited, so we are done. We'll go back, we'll trace back 4 right here, 5, 2, 1. Okay, and 1 will go back to 0, and then we'll be here returning true. Once you return back true, you will increment your count, and then we'll have in this for loop, we'll try to call it on 1, 2, 3, 4, 5, but like we know it's going to return false from right here because they are already visited, so we'll not increment this count anymore. But then once you come to 6, you're going to start exploring 6. 6 is not in your visit set, so you're going to mark this visit. You're going to explore 7. 7 is not in your visit set, then 8, and you're going to trace back to 7 to 6. Here you will be returning true. All right, how awesome was that? And then you will be returning finally, in this case, 2 will be our answer because there are 2 connected components. All right, so that will be it. It's going to be super simple code. I've just already written here, so you can just quit the video and write the solution. Go back to the editor and write the solution yourself. But if you're still confused, stay around because we will be writing the code now. So in this case, our time complexity, I'll write it here. Time complexity will be big of v plus e, that's vertex and number of edges, and space complexity is also same because at max, worst case, we are visiting all the nodes, right? All the nodes of our graph. Or you can change it to n as well because we are given n number of nodes. So let's go back and write this. Convert our thirds to the code. So we'll have a visit set. I'll call it visited. Then let's create the graph. Initially, graph will be, empty list next to each node. Each node for I in range n. Now let's fill it up. So we're gonna visit all the values a and b, these pairs a, b in edges. Okay, so graph a, this key will have b as neighbor, so we're gonna append that b, and then we'll do the same to b. So b's list will have a as neighbors. Okay, now our adjacency list is done. Awesome. Now what do? We're gonna run a for loop for let's call it node in range. We're gonna call it n, and if DFS on node returns true, then we can increment our count. So let's call it connected components +1. Okay, and then finally this is what we will be returning. Okay, and we forgot to initialize it. Not forgot, I mean we're initializing right now as with 0. Let's write our DFS. This is where we will be writing it. It's an inner function, so let's call DFS, which will take a node, and if node in visit, so if node in visited, node in visited, then we return false. Otherwise we will add it to visited. So visited dot add this node. So for now we're gonna start visiting all the neighbors of this particular node. So let's call these neighbors as NEIGH, ni. For ni in a graph, this is where you will be accessing all the neighbors of this particular node. So we're gonna run. We don't have to do anything. We just run the DFS so that we can visit them in this particular call of DFS. Okay, so we'll call ni. Now finally we are done visiting, so you can return true. Okay, and that will be it. Let me just clean up things so that you can see the entire code, all together. This is all the code, and I'm going to zoom out so you can see the entire code, and then we can finally run it. For I in range, that shouldn't have been the kind of typo I do. Alright, so accepted. Now let's write the time complexity. Time complexity, we have already discussed this. It's gonna be v plus e. Remember, v is the number of vertices. In this case it could be n, and e is the number of edges. And space complexity is also same. We are, or you can say it's like we are visiting all the nodes, so it can be just we don't have to mark E. But honestly, I think I would, because I am creating this graph and I am also storing like that reference to the edges, because there is an arc, you can say, like to each A there is an arc to all the neighbors. So this should also be the, although earlier I was just thinking about the visited set. All right, so hopefully soon I'll add this description to AlgoYogi right here somewhere, like you can solve it right here. We have our own code editor, so I'll add it right there. So let's mark this problem solved. See you guys later in the next problem. And this is what I meant when I said we have a code editor. This is the code editor that we have. Okay, but I kind of like stopped it because I have deployed it in Heroku and it was costing me a lot of money. Yeah, so I discontinued it. Anyway, so I will see you guys later in the next video.